In 2013, the European Space Agency's Planck mission, using more advanced technology and different methodologies, confirmed the anomaly's existence. This wasn't an error, it was real. Located in the constellation Eridanus, what scientists now call the cold spot spans roughly 1.8 billion light-years across. To grasp its immense scale, consider that our entire Milky Way galaxy is just 100,000 light-years in diameter, making the cold spot approximately 18,000 times larger than our galaxy. This vast size, combined with its uniform temperature drop, presents a profound cosmological puzzle. The scientific community's response to these findings reflected a growing tension between established models and new observations. Dr. Jao Magwejo, a theoretical physicist at Imperial College London who studied the anomaly, remarked that the cold spot was immediately seen as either a potential major challenge to the standard model of cosmology or a significant statistical fluke. This division highlighted the stakes. Either our fundamental understanding needed revision, or we were witnessing an extremely rare natural fluctuation. What makes the cold spot particularly baffling is its statistical improbability. According to standard cosmological models based on inflation theory, temperature variations in the cosmic microwave background should follow a Gaussian distribution. They should be random, but predictable within certain parameters. The cold spot represents a deviation so extreme that cosmologists estimate its probability of occurring naturally at less than 1 in 50, with some analyses placing the odds at 1 in 500. Dr. Tom Shanks of Durham University emphasized this point. The temperature differences we're seeing are significant enough that if our current understanding of cosmic evolution is correct, this cold spot simply shouldn't be there. The search for conventional explanations began immediately. The first hypothesis suggested that the cold spot might represent a supervoid, an exceptionally large region of space containing far fewer galaxies than expected. This would create the observed temperature drop through the integrated Sachs-Wolf effect as light from the cosmic microwave background lost energy traveling through this void. To test this theory, astronomers conducted extensive galaxy surveys using the Very Large Telescope in Chile and the Anglo-Australian Telescope. They did indeed find a supervoid in the direction of the cold spot, extending about 1.8 billion light-years across. Initially, this discovery seemed promising. However, further analysis revealed a critical problem. The supervoid wasn't empty enough. Calculations showed it would only account for about 10 to 20% of the observed temperature drop. Even the most generous estimates couldn't fully explain the cold spot through the supervoid hypothesis alone. Additional conventional explanations emerged. Some researchers proposed that the cold spot might result from a topological defect in space-time called a texture, essentially a wrinkle in the fabric of the universe left over from the Big Bang. Others suggested an unusually large quantum fluctuation preserved during cosmic inflation. Each explanation initially seemed promising, but ultimately failed under rigorous mathematical scrutiny. The texture hypothesis couldn't account for the specific temperature profile observed, while the quantum fluctuation explanation couldn't explain why only one such extreme fluctuation appears in our observable universe. By 2015, the scientific consensus had reached an uncomfortable position. The cold spot represents a genuine anomaly that cannot be fully explained by any conventional cosmological phenomenon. It directly challenges the standard lambda-CDM model of cosmology, the very framework that has successfully explained nearly everything else about the universe's large-scale structure. We've exhausted the standard toolkit of cosmology, explained Dr. Istvan Saputty of the University of Hawaii's Institute for Astronomy. Either we're missing something fundamental about how cosmic structures form, or we need to consider more exotic possibilities. This has led to a profound reassessment among cosmologists. If our most successful theory can't explain such a significant anomaly, what else might it be missing? The implications extend beyond this single cosmic feature to question whether our entire approach to understanding the universe needs revision. Scientists approach this challenge with appropriate caution. As Dr. Carlos Frank, a cosmologist at Durham University, noted, "Extraordinary claims require extraordinary evidence. We must exhaust every conventional possibility before considering more exotic explanations." But the cold spot is increasingly pushing us toward those exotic explanations. This scientific humility balances with the willingness to consider revolutionary ideas when evidence demands it. Multiple independent observations have confirmed the cold spot's existence. Different analytical methods have verified its statistical significance. Various conventional explanations have been systematically tested and found wanting. What remains is a cosmic anomaly that defies our current understanding. A massive region of space that, according to our best theories, simply shouldn't exist in the form we observe it. It stands as a humbling reminder of how much we still have to learn about the universe, despite our remarkable progress in cosmology over the past century.